can't just tag people, or there's not that many ways to get that information. And those are the types of things that we're thinking about. I'll give some more examples.
I'll give you an example beyond the New York Times. There are big rallies in Washington.
Right.
Okay. So you hear all different kinds of counts.
Yeah. Yeah, and that's
police estimate this.
Yeah,
price,
and there's nobody ever agrees, because there's really not, there's no, it's impossible to agree, because there's no accurate ways of doing it.
If you can give good answer, that would be great.
Well, we'll see what we can do. I mean, we're looking at that. Okay, so but I think so. You've got the point by now. It's the idea is it's sort of like making an analogy with physics. Modeling a crowd by sort of tracking each object it would be the equivalent to trying to predict the state of a gas. By sort of keeping track of what its particle is doing. Typically when we do physics, we don't really do that. We look at macroscopic properties of the gas. What is the temperature, the pressure, and the density, and so forth. And so similarly, typically when we're talking about crowd management problems and things like that, you're interested in macroscopic properties. What's the congestion, what's the density of the crowd in different areas of the city or whatever. What are the flows like, where are people going, things like that. And those are all sort of macroscopic properties that require macroscopic models. Okay, so we've been looking at how can we model these types of, video from these types of scenes with macroscopic models. So one model that we actually, we started by trying just because it was in the literature, it's kind of interesting, and it's actually given some quite interesting results, is the dynamic texture, which is a model that was, came out of Stefano Sovato's lab at UCLA, and which is basically, an holistic model for the appearance and dynamics of a scene. Okay, so you have a video, and this is a model that will model both the appearance and the dynamics of that video. It's a generative model. It basically says that video is a sample from a linear dynamic system, and the property that attracts us to us is that it's really like a sort of a global model. There's no object segmentation or tracking involved. It's sort of a model that keeps, capture, say, the global properties of moving textures and things like that. That's why it's called a dynamic texture. And Stefano and his students, they'd already shown that it can be applied for a number of things. So we were certainly not the first ones to use this model. And I'll tell you a little bit in more detail what the model is, in case you don't know. And there's many ways to think about it, but it's really a simple model, and the easiest way to think about it is as a PCA model with memory. So if you've done any machine learning, PCA stands for principal component analysis, and the easiest way to think of this is sort of PCA, principal component analysis with memory. So what do I mean by that? Okay, so the model is a linear dynamic system, and if you know what a linear dynamic system, then you're all done. That's just what it is. If you haven't seen linear dynamic systems, you can think about it in this way. So there's a pair of equations. There's a set of observed variables. So this is the graphical model, in case you're more familiar with that language. So there's a set of observed variables over time, which are video frames. Okay, the video frames are the things that get observed. Okay, so they're samples from observed variables. And then there's a set of hidden variables which encodes the state of this linear dynamic system. Now, if you look at these equations, okay, if you look at y, which are the observed variables, they're related to the state x, basically by this linear transformation. Okay, so you can think of this as a principal component type of decomposition, where you can think of the state as the coefficients of the principal component analysis, and then the columns of this matrix C get linearly combined by these coefficients, and they're used to reconstruct Y. So if you actually try, learn the model on the video, so these are what the columns of this matrix C look like. they look like the eigen, they're the the eigen images for this video, the frames in the video. Okay, and then there's a few more things here. There's like noise. So if you want to be technical, it's actually more like factor analysis and principal component analysis, but it's not a big a deal. Okay, so that's basically this part of the model. Then beyond that, what we have is that we have a first order Gauss-Markov chain for the state, which is this part of the graphical model, and that just means that the model also keeps track of how the trajectories in the PCA space evolve over time. So that's what's shown here. So the vector x is a vector of coefficients, so they're the weights to combine these basis functions. And so this part of the model, what it does is that it keeps track of the evolution of these coefficients over time. So you can literally think of this as principal component analysis with memory, where in addition to computing these principal components and figuring out what are the projections of the data on those principal components, we also keep track of how the principal components coefficients change over time. And because of that, it captures both the appearance and sort of the dynamics of the sequence. And we can use this model to do interesting things in terms of modeling texture globally, for example, or modeling this type of video.
I have a quick question. If you didn't have, if you had instead of the picture, the actual video, like a simulation, would that correspond to having 0, W, and V? There was no noise. Okay. Now, if you did the instead of having the actual video, you have a simulated situation.
Well, you from this model you could actually let me actually show that afterward. There's one question there about whether this is like natural video or not,
right,
or sort of artificial generated. This video, even though it looks natural, it could be just simulated from the model.
Can you do a simulation such that you get W and V 0?
W.
Eliminating W and V so that
Yeah, you can set them to 0. That reduces the variability of the model. It makes it more deterministic. So this allows us to account for like small deviations from so the model is not like a law. It's like it's like the mean, the average.
My question: what was the importance? If you get rid of those, you still have.
Yeah, you still have a model. You still have a model,
okay,
but you won't have any flexibility to to adapt it to video where the fit to the model is not exact. Okay. So here's an example of using this model on this video. So here's 3 video sequences from this highway traffic. And here, what we did is we learned the parameters of the model from the video. And what I'm going to show you here is just like samples from the model. Okay, so these have nothing to do with at this point, the algorithm doesn't know about the original video anymore. We just learned the parameters from here, and now we sample new video from the model. And in fact, this one is going to extend longer than the original one. It's not even sort of directly comparable. And here you will see the same, but without the principal component that accounts for the background. And that's just so that you can look at the dynamics more easily. Okay. Let me actually play this. What we see is that you can look at the thing and you see that you see like cars moving in this highway. It's not a perfect reconstruction, and we would not want a perfect reconstruction because that means we like totally overfitting to the video. But you see that it does capture important elements of both the appearance of this video and the dynamics. Okay, how things are moving. So, for example, you get this clear difference. Objects are moving faster at the video at the top, and here it also appears that they're moving faster, and here it appears that they're moving slower.
Can I count here at this level? It becomes easier.
We'll see.
Okay.
Excuse me? So in the model you described, are the observed variables independent from time slice to time slice?
Well, the observed variables there. Well, the graphical model is this. Okay, so there's dependency. So if this variable is known, then they're independent. Okay, but if this variable is not observed, then there is dependence. Okay, between the variables. Okay, and that's why that you get this note, and that's visually. That's why this. If you look at this, this is like there's a smooth motion. It's not random, and that's because there's that dependence. What comes after depends on what came before. Okay, so there's, however, one problem with this dynamic texture model, and the fact is that this is a model that assumes uniformity. So it assumes that the whole video is a sample from this linear dynamic system. And in practice, that's usually not the case. What happens is that we have a combination of things happening. So for example, if you look at this video of pedestrians moving on this walkway, some people are going away from the camera, and some people are coming towards the camera. So what you really have is you have two components. You have a flow. You have two different flows. What's more important is that the semantics of the scene are tightly connected to those flows. It is the fact that there's two different flows that are really important if, say, we want to figure out how many people are going away versus how many people are coming this way. Okay, so from that model that gets hard to figure out. So one simple extension that we've worked on, it's called a mixture of dynamic textures. Okay, and the idea is again simple. You have a video. Here's a little cartoon where I have a video that has like 3 different textures: water, smoke, and fire. And what I'm going to do is I'm going to model the video locally. So I'm going to extract spatial temporal cubes from this video. And then I will have spatial temporal cubes of water, spatial temporal cubes of smoke, and spatial temporal cubes of fire. And then I'll fit a mixture of these linear and dynamic systems. So I will explain the video as a mixture of these linear dynamic systems. So I'll have 3 dynamic textures or 3 linear dynamic systems, and then at each point in the visual field, I will select one of them. And that will be responsible for, say, the water pixels, or the smoke pixels, or the fire pixels. Okay, so that becomes a mixture of dynamic textures. It is a simple extension of conceptually, it is a simple extension of the linear dynamic, the dynamic texture. So now we have a number of linear dynamic systems, and you can see here the equations. The difference is that now the parameters are indexing by z, which is a variable that selects one of the models. Okay, so there's a multinomial random variable that each point in time selects one of the linear dynamic systems, and then the video at that point in time or in space is sampled from that linear dynamic system. And so, the way to think about it is that now I have, 2 different of these, PCA with memory models, and at different points in time, I can sample from each of them. If I want to have a traffic modeling system that, say, accounts for the fact that during the day there's different levels of congestion, I can have a model that has 2 components, say, one for not very congested, and another one for congested, and during the day, the model figures out like what of these dynamic systems is more suitable for the traffic at that instant. Or I can do this on a cube basis, like I've shown you in the previous slide, and I can learn. I can apply this. I can select between these different models at the different location of the visual field, and so that allows me to sort of segment the scene into different types of dynamic textures. Okay, so just a little bit on how this is done. So as usually, this is a problem of learning the model, the parameters of the model is a parameter estimation problem. So we have these video sequences. The thing that's a little more complicated than